To continue with our study of graph theory, let's look at some simple examples. Well, maybe not so simple. As you look at this looks rather elaborate. There are lots of vertices shown here and lots of edges. This is a graph of my wife's local Facebook network. And each vertex here represents a Facebook friend of my wife. Now, there's no node for my wife at all. It shows her Facebook friends. And what an edge means is that those two people who are involved are themselves Facebook friends. So if you have a pair of vertices, there either is an edge or there is not an edge between them, and it's simply determined by whether they are or are not Facebook friends. So just to illustrate that, for example, I've shown the vertex representing our daughter, who is also on Facebook. And you can see there are lots of edges coming out from her vertex and going to many other edges. And what this indicates is that among my wife's Facebook friends, many of them are also Facebook friends of my daughter. On the other hand, you can see that there are a lot of Facebook friends of my wife that are represented by a vertex of degree 0. And why is that? Well, that's because these are people that are friends of my wife, but they aren't friends with any of her friends. That doesn't mean that they don't have any friends at all. It's simply that if you look only at people who are Facebook friends of my wife, that this particular person, represented by a vertex of degree 0, is not a friend with any of her other friends. So that shows how graphs can represent networking on the internet. Here's another, maybe more practical example. There are 4 basic human blood types. And when people started giving blood from one person to another, as is sometimes needed in operations and for other purposes, they discovered that sometimes this doesn't work. And the reason is because of these 4 basic human blood types. And it was soon worked out what the rules were. There were certain circumstances where it was not a good idea, it was not okay for one person to give blood to another. So this graph actually shows all of that for the 4 basic human blood types, which are called O, A, B, and AB. So we have here a graph with 4 vertices, which are shown by those letters. And then we have the edges. Now these should be directed edges because we're concerned with, for example, can a person of blood type O give blood to a person with blood type B? And if so, we want to draw an arrow from O to B as we have done. In fact, let me show you that arrow. I'm talking about the arrow which is, let me do this, right here, okay, right here. Notice that there's not an arrow going back the other way. That is to say, a person with blood type B cannot give blood to a person with blood type O. In fact, as you may know, type O is universal donor. So a person with blood type O can give to a person with blood type A, as indicated by this arrow, or a person with blood type B, or a person with blood type AB. And in fact, we should also draw, as we have, a loop to indicate that a person with blood type O can give to another person with blood type O. Now again, all of these rules could just be written down, but I think the graph actually is a clearer way of presenting this information. You instantly see the 4 blood types, and you can see the circumstances where it is okay for one person to give blood to another. Another example is the way that molecular structures are often represented in chemistry in this manner of a graph. Okay, the vertices in this example represent atoms. Now, rather than draw dots, we actually indicate what kind of atom they are, because as you know, atoms come in various types according to the kind of elements that they are. In this particular example, we just have C and H representing carbon and hydrogen. And then the edges indicate chemical bonds. Now, this is a very direct way to indicate a chemical bond. If you're really a chemist and want to understand this more carefully, you have to understand a lot more about what that represents. And eventually, if you're extremely sophisticated about this, this will even lead to concepts of quantum mechanics. But we don't need to worry about that, and for many purposes, all you need to know about the structure of a molecule is what are the constituent atoms, which are going to be represented by vertices, and what are the bonds, which are represented by edges. Notice, by the way, that sometimes we have multiple edges in this example. We have double edges, and in fact that's because there's something called a double bond. There really is two bonds, or I should say there really are two bonds between some of the C's. And one rule that must be satisfied if you're drawing something that can really be a molecule is that the degree must be a specified number depending on the type of atom you've got. So for example, if you look at the H's here representing hydrogen, you'll notice that each one of those vertices has degree 1 because that's the correct number for hydrogen. In chemistry, one doesn't say degree, however, one says valence. That's the word that's used in chemistry, but you can think it's really a graph theory concept. It's the same as our concept of degree. Similarly here, if you look at the carbon atoms, there are 6 of them, you'll notice that each one of them has degree 4 when we correctly count the degree. That is to say, for the double edges, we count 2 in every case. This, by the way, is a molecule that's called benzene. Let me also follow up a bit on an example that you did in your recitation. On the left, you see the information that was handed to you in the recitation. This is information about certain stations in the subway system, ones that I had to use when I was trying to get to work many years ago. I was trying to get from my house out to work. And these were the relevant stations, 103rd Street, Columbus Circle, and so on. And one way to indicate whether it's possible to get from one station to another is to record the information as I have on the left in a little table. So for example, let me show one of these examples here. Here is an X, which indicates that it is possible to travel from Columbus Circle to 50th Street on a train. That is to say, at the Columbus Circle station, there's a way of getting on a train and later on getting off that train at the 50th Street station. On the other hand, it's not possible to get on a train at 103rd Street and get off at 34th Street. There is no such train. So this really has all the relevant information, but if you were faced with the problem of getting from one station to another, I think you would find this a rather inconvenient way of thinking about the information and recording the information, which is why I hope that in the recitation you all saw that it was easier to record the same information in a graph. So here, instead of having the stations indicated by rows and columns, they're indicated by vertices. Here's the vertex representing 103rd Street. And then rather than draw X's in a table, what we've now drawn is we've drawn edges, which actually seems a much more natural way to represent the information. So for example, the fact that you can get from Columbus Circle to 50th Street is indicated by the edge right here, which I'm now circling. Okay? There is an edge there. On the other hand, there is no edge going from 103rd to 34th because there is no such train. Now looking at this, it's much easier, I think, to figure out how it is that I could get from my home, which is 103rd, to work, which is at 169th Street. You were asked to find what? I mean, what was the problem you were asked to do? You were asked to find the minimum length of a path from a vertex at the top to a vertex at the bottom. That was the problem of saying how many trains it required for me to go to work. And then, given that it took 3 trains, in other words, the minimum length of a path was 3, you were supposed to find all such paths, and in fact, there were 5 of them. Now, before I stop looking at this example, I want to point out that, again, The graph only records information about getting from one station to another. In other words, whether you can do it. It doesn't actually tell you the pathway that you would take. And in particular, this would be totally useless as a map, say, above ground. For example, if you've ever been to New York and you wanted to walk, say, from Times Square to Rockefeller Center, which is a very easy walk, you will never in that direct walk go over 34th Street. Okay, this is not an accurate representation on the ground of how these things are located. It simply records the information that's relevant when you want to take the subway. What you care about is what station is connected to what other station by a train.